Yeah, I see a very clever student raising their hand in the first row. That'd probably be best because the people on my screen are all extremely tiny.
All right, welcome everyone to the Wednesday morning session. Our first speaker sadly could not be here in person, but we're very happy to host her giving a Zoom talk. Carolyn Chun from Maryland will speak about graphs embedded in surfaces and delta-matroids.
Thank you very much, and thank you to the organizers of this meeting. I was really looking forward to it, and I've been enjoying it from afar. I've listed here some of the people that I've worked with on Delta Matroids: Joe Bonin, Deborah Chen, Ian Moffett, Stephen Noble, and Ralph Ruckerman. Um, I've worked with Tyler Moss and Jakayla Robbins on, we looked at some ternary delta matroids, but never published on that, so they're not on this list. Um, it turns out that a lot of interesting objects are matroids, and please feel free to interrupt at any time if there's any questions. Matrices are matroids, graphs are matroids. Every graph that's plane has a dual that's a graph, but every graph is a matroid and every matroid has a dual. So duals of graphs are also matroids. Those are some interesting things. Uh, many interesting objects are delta matroids. So skew symmetric matrices over a given field, embedded graphs or ribbon graphs, partial duals of graphs. And there's a couple of um, interesting things. DNA recombination in ciliates is related, that's related to delta matroids. Higgs lifts between matroid quotients. Matroids are delta matroids, it turns out. And a lot of people are interested in matroids in this audience. So I'm going to talk about graphs that are embedded in surfaces, but I'm going to think of them as being ribbon graphs, which is something that Ian Moffett would love to explain in more detail. But I'll give some broad strokes here. You take a graph that's cellularly embedded in a surface. Here I have a surface that's a torus. I've taken a graph that's cellularly embedded. That means that every face is deformation retractable to a disk. So there's no handles, there's no cross caps on any of my faces. And then what I do is I cut the face out of the surface. Or another way to think about that is you can thicken the vertices and edges and then get rid of the face. This ribbon graph actually preserves all the information from the graph that was embedded in the surface because it's unambiguous to reattach that face that we've just cut off. And something that we're going to care about here is the number of boundary components, which is the number of missing faces from a graph. That's something that we'll care about sometimes, particularly when the number is one. So I want to point out that this is a really special kind of ribbon graph that has exactly one boundary component. And I'll trace along the boundary component just to show what it is. You go around the edge of the ribbon. So I've gone around that little loop. I'm going around the left side of it. I come back to the vertex, and now I go around the inside of the big loop. And then that brings me to the right side of that little loop, and I can trace around that. And then I can go around the outside of the big loop, and I come back to where I've started. That means I've completed my boundary component, and actually every edge of every edge has been accounted for. So this is a ribbon graph that has exactly one boundary component, which is a special kind of ribbon graph called a quasi-tree. So this ribbon graph came from what surface was it embedded in? Cellularly embedded. Does anybody? A sphere. I don't know who did that good answer. It sounded maybe like it was Dylan. Um, was it Dylan? It was Rutger? Oh, thank you, Rutger. Stop impersonating Dylan, please. Uh, this graph was embedded cellularly in a sphere, and now I can take its spanning trees, and those happen to be the quasi-trees. If you think about a spanning tree, that is a graph that has exactly one face, a connected graph that has exactly one face. And the spanning trees, which are the quasi-trees of this ribbon graph, those are a special collection of sets because matroid theorists see that collection of sets and they think, actually, those are the bases of a matroid. So what happens if we take a more interesting surface? Here I've got a graph that was embedded in a non-orientable surface. And now I take the quasi-trees of this graph, and I'm going to get all of the spanning trees as quasi-trees because those will still have one boundary component, or they'll correspond to subgraphs that had exactly one face. But I actually, because of this twist, this half twist on edge 5 that I've illustrated here, I can get quasi-trees that have 4 edges. So if I look at the set 1, 2, 3, 5, I can think about counting the boundary components there. Well, if I go around the left side of 1 and 4 is not there, then I'll be able to get to the right side of 1, go along the top of 5, which brings me to the interior of the cycle. I can get around the interior of the cycle, and that brings me back to the outside, back to the top of 5. I go around the right side of 3, the bottom of 2, and I come back to 1 where I started. That's one boundary component. So the set 1, 2, 3, 5 is a quasi-tree. So these are the quasi-trees of this ribbon graph. And you look at those, and there's a problem. A matroid theorist will look at these sets and they'll say that those are not the bases of a matroid, because what's the problem here? There are different sizes. Was that Peter? Oh, well then. There are different sizes. My bases and my matroid are equicardinal, but these actually are going to be feasible sets of a delta matroid, which you can write either with the Greek letter or with the English spelling. So trees in graphs give me bases and matroids, but we all know, or many of us know, that not every matroid comes from a graph. Quasi-trees in ribbon graphs give feasible sets of a delta matroid, but analogously, not every delta matroid comes from the quasi-trees of a ribbon graph. The ones that do are a special class called the ribbon graphic delta matroids. There's a mutually enriching relationship between graphs and matroids that is analogous to the mutually enriching relationship between ribbon graphs and delta matroids. And that's a very rich area to think about. Delta matroids generally, they don't have to come from ribbon graphs. They have to obey these two axioms. So if I have a pair, if D is a pair, I've got my ground set E, and I've got my collection of subsets of E, F. Those are my feasible sets. Then I've got a delta matroid as long as you have something in the feasible sets. And the symmetric exchange axiom holds for the collection of feasible sets. The symmetric exchange axiom, matroid theorists may recognize this, but maybe they've seen the minus sign where I've got this triangle, which is the symmetric difference operator. So the symmetric exchange axiom says when I have F1 and F2 that are feasible, I have an element E and their symmetric difference, so it's in exactly one or the other, it's not in both. Then there's an element F in the symmetric difference, so that F1 symmetric difference EF is also feasible. I do not require that E and F be distinct. They may be the same element. So this was defined by André Boucher in 1986. And this, as long as we satisfy these axioms, you have a delta matroid. And again, quasi-trees for ribbon graphs will satisfy these axioms. So now I've got something called a delta matroid example, because one of these is a delta matroid and one of these is not a delta matroid. when I think about feasible sets in a delta matrix, because they have different sizes, I often think of them as I think of the smallest ones being the first row, and then the next largest in the next row, and I like to put them in size order when I write them down, almost like a restriction of the Boolean lattice or something. Um, so Z and D they're both set systems. They both have ground set ABC. Z has exactly two feasible sets, the empty set and the full set ABC. D has these seven feasible sets. Which one is which one is not a delta matroid? Does anybody have a, I'm sorry? Oh, yeah. So there's a hint in how I named them. And yes, Z is correct. AKA, am I the only one who calls it Z? Um, if I take F1 to be the empty set and F2 to be the full set, and A is in their symmetric difference, therefore, if the symmetric exchange axiom holds, then there should be an element F in the symmetric difference of the empty set and the set ABC, such that the empty set symmetric difference AF is feasible. However, that would be either a two-element feasible set in the case that A and F are different, or a one-element feasible set in the case that A is equal to F. And Z has no such feasible sets. Therefore, Z is not a delta matroid. D, on the other hand, is a delta matroid. And this is an example that we'll see again in a little bit. So matroids follow these same axioms, but something is missing. So this is a copy of my slide about delta matroids, except I've changed the D to an M. M is a matroid if it as a ground set together with a collection of bases. The bases have to be non-empty. I mean, we have to have at least one basis, and the symmetric exchange axiom has to hold for the collection of bases. And I would like one more axiom. Does anybody have another axiom to suggest? Equicardinality, yeah. Who said that to me? Right. Nicely done, Ricker. You sounded a lot like Dylan that time. They should all have the same size. That's the only difference between matroids and delta matroids. So you've heard the quote, if a theorem is about edges and cycles for graphs, then it may exemplify a more general theorem for matroids. Well, if a theorem about edges and quasi-trees holds for ribbon graphs, then it probably exemplifies a more general theorem about delta matroids. And if we have a theorem about elements and bases and matroids, that may also exemplify a more general theorem for delta matroids. And there may be a couple more authors who were involved who discovered matroids. I've drawn some illustrations of duals. I want to talk about partial duality, so I'll start with full duality. If I have a graph embedded on a sphere, like the graph with black edges and vertices on the left, then I can take that sphere and think of the dual of that graph by taking, instead of vertices and edges, I take my faces, and now two faces are adjacent will give me two vertices being adjacent in the dual. So I take each face, and that gives me a vertex in the dual, and I connect two edges when those faces are adjacent. So every edge gives you a new edge in the dual, and every face gives you a vertex. I've drawn a torus here, and the torus with those two loops, it turns out it's self-dual. The dual that is, well, it has one face, so it's one vertex, and it's got two loops. So for embedded graphs, taking a dual, I'm sorry, was there a question or comment? Okay, I'm sorry, I thought I heard something. Duals for matroids are done by taking, and you may think, well, you should just use the ground set minus each basis. But here I've used the symmetric difference operator. So to get the matroid, to get the dual of matroid M, I take, which is I call M star, I'll take the same ground set and then I'll replace each basis with its complement. I'll take each basis and replace it with B symmetric difference E. Matroid duality generalizes plane graph duality, which is to say, if G is a plane graph, then the dual of the matroid of G is equal to the matroid of the dual of G. And there's some interesting classes of objects that are closed under duality. Plane graphs are closed under duality. That's an interesting class of objects. The matroids representable over a given field is closed under duality. Matroids, the class of just matroids, is closed under duality. But what is so special about the whole ground set? That's sort of the question that partial duals addresses. If I take a subset of the ground set that's different from E, and I just take the symmetric difference of each basis with the symmetric difference, the symmetric difference of the basis with a random set, I might not get equicardinal sets, but it turns out what I get will be a delta matroid. So for delta matroids, I will stay within the class of delta matroids, but for matroids, I may leave the class of delta matroids if I start doing partial duals. A partial dual is done by taking a subset A and taking the symmetric difference of every feasible set with that subset A. So the partial dual with respect to A, I write as D star A, and I just take the same ground set and I take the symmetric difference of each feasible set with that set that I'm interested in, A. Delta matroid partial duality generalizes ribbon graph partial duality. That is, if G is a ribbon graph, then the partial dual with respect to A of the delta matroid of G is equal to the delta matroid of the partial dual of G. And I've written the set A as a superscript for G to indicate that I'm going to take that partial dual within the graph. I'm not going to illustrate how to take a partial dual within a graph. It is a graphic operation, and I've seen Ian do it, and I still have yet to master being able to dualize a subset of edges within a graph, but it is a graph operation. So it turns out there's some interesting classes of objects closed under partial duality. Ribbon graphic delta matroids, because it is a ribbon graphic operation. So you don't leave the class of ribbon graphs when you do this partial duality operation. The delta matroids representable over a given field are closed under partial duality. The partial duals of matroids, and then delta matroids generally. And partial duals were defined by S. Shmutov for graphs on surfaces in 2009. I want to introduce the partial petrel operation. It gets a bit hairy. We'll get through it together. So I've got two graphs side by side. They differ by a half twist on 5. That's the only difference between these two graphs. I've written the sets of feasible sets beneath each graph. And I've renamed these graphs. The one on the left is G, and the one on the right is G with a superscript pi of this set 5. Pi tells me I'm taking the partial petrel on the edge set 5. So when I take a partial petrel, I add a half twist to a set of edges, to each of the edges in a set. Here I've just taken the single edge 5 and I've added a half twist. As we saw before, in this case, it gave us 4 more feasible sets. Loop complementation is purely delta matroidal. It can be done in any delta matroid. It doesn't have to be a ribbon graphic one. And loop complementation is a really useful operation in delta matroids. Beginning with a set of feasible sets in a delta matroid, loop complementation is done with this plus operation, and it changes the feasible sets. I'll show with an example. if I begin with the feasible sets that I had for that graph that was on the left, what I've done is I've separated out the feasible sets in red that avoid 5 and the ones in blue have 5. And what I do when I take the loop complementation with respect to 5 is the feasible sets, the new set of feasible sets, I'll include every feasible set that avoided 5. So that's the feasible sets in the delta matroid. Delete that edge 5. So every red set is going to be in my new set of feasible sets. And I add to that set this sort of, it looks a little bit complicated. So what I do here is I take the feasible sets that have 5, and I remove it. So the blue one's -5. Symmetric difference, the feasible sets that avoid 5. But then to each of those, I add the element 5. So this is what happens step by step for this second half of this this line right here. I get all the sets that avoid 5. I get all the sets that had 5, but I've taken 5 out. Now put 5 back in and put them all together. And I add those to the red sets that were here. So these are the feasible sets. I've written them here on the top right that we get by doing loop complementation. And surprise, surprise, they're exactly the feasible sets for that ribbon graph that we had on the right there. So it turns out that loop complementation, which is a delta-matroidal operation, it corresponds to partial petriol within the ribbon graph, which is cool. And it turns out that it's sort of the right way to think about it. So the class of ribbon graphic delta matroids is closed under taking loop complements. We know this because I just showed you that taking a loop complement is the same as taking a partial petriol, and a partial petriol is a ribbon graphic operation. And the class of delta matroids closed under taking loop complements is called VF safe, and it's a special class of delta matroids. Back to the example, it turns out that D loop complement A, loop complement B, loop complement C gives Z. What does this mean? It means that we may leave the class of delta matroids once we start doing loop complements. So taking the loop complement on D, we may end up leaving the set. So the set of VF safe delta matroids is a special set. I'm running low on time, so I will. We have minors in matroids obtained by doing deletions and contractions. We consider a 3 minor to be where we do deletions and contractions and loop complementations, because a delta matroid that is obtained in that way from another delta matroid is actually highly related to that delta matroid. Jim Geelan and Sang-Il in 2009 found a set of 116 excluded minors up to partial duality, excluded minors for ribbon graphic delta matroids, which is super cool. But it turns out that if you consider these 3 minors, then the list is actually only 8. There's 8 families of excluded minors for ribbon graphic delta matroids. And this is my last slide. I try to get through it quickly. So binary delta matroids are VF safe. So that's a cool class of delta matroids that have skew symmetric representations over the 2-element field. And that's Breider and Hoochboom. And they also prove that quaternary matroids are VF safe. So you don't leave that class by doing loop complementations. Steve Noble, Irena Pavoto, and Gordon Royal showed that they found a set S so that a matroid is VF safe exactly when it has no minors. That is a partial dual in S. So they found the excluded minors for a matroid to be VF safe. And it turns out this is such a nice, I really like excluded minor characterizations. And the class of delta matroids that are VF safe can be characterized by a single excluded minor, it turns out, when we consider 3 minors and twisted duals. So the bottom result is this is Z. This is just Z. Okay, thank you very much.
Thank you, Carolyn. For technical reasons, if you have a question, I'll relay the question to Carolyn rather than giving you the mic. So, are there any questions? Yeah.
So when you're talking about this representable case, is it represented by the only symmetric matrices?
Did you hear that, Carolyn? So the question was, when you're talking about the representable case, are you only represented by symmetric matrices?
Yes, skew symmetric matrices.
What about the skew symmetric matrices?
She just
So
said skew symmetric, I think. Oh, sorry.
So the representation for the delta matroid that is representable over my field, we get it by taking a skew symmetric matrix where the columns and rows are labeled by the elements in your delta matroid. And then if your principal subdeterminant is non-zero, then you have a feasible set.
Are there any other questions?
It would seem like then every representable delta matroid over any field should have the empty set as a feasible set, and that is not true. It's that your delta matroid has a partial dual that has a representation. So it's basically what I said, but with a twist, literally.
Are there any other questions?
Maybe you should. Three minors and
You can leave the class. I mean, I think they live inside set systems, and so Z is a set system, but it's not a delta matroid. Like exactly like you said, the taking loop complementations may leave the class. Yeah. So it's something that we do in delta matroids, but it doesn't preserve being a delta matroid. It's a safe operation to do inside every delta matroid that has no three minor isomorphic to a twisted dual of Z. Otherwise, it's a little bit risky. So you want to view every delta matroid as being equivalent to all of its partial duals? Yeah. Oh, that's interesting. I mean, so in the same way that matroid theirs don't distinguish between a matroid and its dual, a delta matroid theirs doesn't necessarily distinguish between a delta matroid and its partial duals. So sort of in practice, I think that that's the case. But when you want to get a representation, you do need a partial dual that has the empty set as being a feasible set. So that's sort of special. That's called I think that's a normal delta matroid. I'm not sure I'm answering your question. I'm not sure. I think I need to understand your question better. So maybe I'll have to ask you some more about that. Thanks very much.